Greetings everyone. In today's video we will be quickly going through the solutions to exam 2. I'm not going to spend a bunch of time on them as they have been posted on Canvas along with the exam itself. Okay, so let's hop right into it. Question 1 was, of course, to calculate a Reynolds number. I'm not going to spend any time going over that. Please look at the solutions. The number you should have gotten for this with the correct number of significant figures is 4540. Question 2, true false. The work required for adiabatic compression is greater than the work required for isothermal compression. That is absolutely true. The fanning friction factor is not a function of the viscosity of the fluid for flow in hydraulically smooth pipes. That is false. For hydraulically smooth pipes, K is equal to 0, but my fanning friction factor is a function of the Reynolds number, regardless if my pipe is hydraulically smooth, and the Reynolds number is a function of viscosity, so that statement is false. Part C, the brake horsepower is the amount of power delivered to the fluid by the pump. That is false. Right? The brake horsepower is not the amount of power delivered to the fluid by the pump. That is the hydraulic horsepower. Part D, the affinity laws can be used for detailed pump calculations. That is false. The affinity laws should never be used for detailed pump calculations. Number 3, Part A, for centrifugal pumps, what is the physical significance of HS? HS is the total dynamic suction head, which is the absolute pressure at the suction port of the pump. Part B asks, why is it necessary to have a pressure relief valve installed on the discharge side of a positive displacement pump? The idea with that is that a pressure relief valve is necessary to ensure that pressure on the discharge side doesn't build up because the positive displacement pump is pumping against a closed valve. Right? Writing an answer to say that the pressure relief valve is there to relieve the pressure, that's given. Right? That's why it's called a pressure relief valve. There needed to be something more to your answer that indicated why the pressure might be building up on the other side of the positive displacement pump. A couple other things that I saw was the thought that maybe the positive or the pressure relief valve was inside the positive displacement pump. That's not what I was describing. What we're describing here is some scenario where I have a pressure relief valve downstream, so that if somehow someone comes into my plant, they close that valve, my positive displacement pump is a constant flow machine, meaning that regardless of what that downstream pressure is or what the pressure is on the discharge side of my pump, my positive displacement pump will continue to pump, eventually causing either the pipe or the pump itself to break. You can also think about that graphically. If I plot head versus capacity, what I find for a positive displacement pump is that the capacity itself is relatively independent of the head or the downstream pressure of the pump, or the downstream pressure against which the pump is pumping. On the other hand, for centrifugal pumps, I get a curve that you see in the light blue. What do I have in a centrifugal pump? Well, this would be my typical operating window, there would be some minimum head, but then down here what you see is that at a flow rate of 0, we have what is called the shutoff head. Right? The shutoff head is the head or pressure at which the positive displacement pump, the shutoff head is the pressure at which the centrifugal pump will no longer produce velocity. Right? The velocity here, or the capacity here, will be 0. This essentially occurs because I have gravity acting against my pump on the discharge side. I eventually get to the point where that gravity causes my fluid to no longer flow. So I, in a sense, have a safety relief or shutoff valve inside my positive displacement pump, right, based on this shutoff head. Hopefully that makes a little bit of sense. My next question, 3. I have a single-stage compressor. Air comes in at 16.4, leaves at 131.2, and a temperature of 285.5. I am told this undergoes polytropic compression, and I have a polytropic index of 1.32, so N here equals 1.32. If the work done per mass is 180 BTUs per pound mass, what is the efficiency of the compressor? So the two equations that I needed to solve this problem are shown above. I need this equation because that equation allows me to solve for TA, which I can then use to solve for the density of the fluid entering the compressor. I can then take that density, feed it back into my polytropic compression equation, and solve for the efficiency of the compressor. Units in this problem are very important. Many of you got the incorrect answer because you did not pay attention to the units in the problem. I have a density in pound mass. I have a pressure in pound force. That pound force is also, or the important thing about that pressure is we're also looking at that per inch squared. Over here on this side of the equation I have feet squared, seconds squared, so I need to make sure that I get rid of those inches squared. That's where this conversion comes into play. And then my other concern here is that I have a pound mass and a pound force. I need to do a conversion between those two. Therefore, I needed G sub C for my problem. Right? That's a very, very important part of this problem, that you make sure that you account for the fact that you have differences not only in the length scales, but also that you have pound force and pound mass in the equation, and you need those two things to cancel. If I've done all of my math correctly, I end up with an efficiency of the compressor of 0.46. Moving on. Okay, 5. We are designing a new acetone system. You have been tasked with calculating operating parameters for a new process where acetone is being pumped from a pressurized holding tank to a pressurized reactor. As such, you have been provided with a proposed schematic for the process. That's somewhere back here. Here is my schematic. I'll back out of this so we can kind of see it. I have a pressurized tank on the suction side. The liquid level inside that pressurized tank is 55 feet below the center line of my pump, and I am pumping that into a pressurized holding tank or reactor. I can't remember what I said. And that liquid level is 30.5 feet above the center line of my pump. You're given information about the specific gravity and the viscosity of the fluid, and you are also given information about the piping material itself. Okay, biggest thing to notice about this problem. Well, let me finish reading the problem. The desired capacity of acetone in the system is 900 gallons per minute. The pressure gauge on the holding tank, right, that's the holding tank, is 75,009.8 pascals. Holding tank and the reactor are large enough that the change in liquid levels in each vessel is negligible. You're given information that could be helpful in the problem. And part A says, based on the initial design criteria, will cavitation occur? So the question I am asking here ultimately, is the net positive suction head available for my system greater than or equal to the net positive suction head required for my system plus some safety factor, which for us we've assigned to be 2 feet. So this is what I'm trying to answer here. If this is satisfied, if this is satisfied, then no cavitation will occur. So that's the question we want to ask ourselves or answer. We need to find the net positive suction head available. We need to compare it to the net positive suction head required and see if that number is larger than the required value plus 2 feet safety factor. So what I need to take away from that is all I care about is what is going on the suction side of my pump. I don't need information about the total dynamic head. I don't need information about the discharge side of my pump. All I am concerned with is calculating the net positive suction head available, and the parameter I need to calculate that is the total dynamic suction head. So here's the equation for total dynamic suction head. Right, you'll see I work through the problem. The first thing I do is calculate a Reynolds number. This is why I stress Reynolds number calculations. These will pop up constantly. These will become just as prevalent when we get into convective heat transfer. So please, 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 please make sure that you understand how to calculate a Reynolds number correctly. From that, I'm given information about my pipe, so I calculate a K over D value. I use figure 510, and I can calculate my fanning friction factor. Based on my volumetric flow rate, I can also calculate a velocity of my fluid. And so I plug all of that information into the total dynamic suction head equation. Pointing out a couple key things here. First, there is a negative in front of that term. Why? Liquid level in tank on suction side is below the center line of the pump. Right? We know when the liquid level is below the center line of the pump, this needs to be a negative value in front of your S term. I have my kinetic energy term here. I take my fanning friction factor, I plug it in there. I'm told the total length on the suction side is 95 feet. What am I accounting for with the 12.5 and the 8? Oh, not in the right thing. Here we go. I'm accounting for the fact that I have one 90-degree elbow and I have one valve. So I'm given the equivalent length of the valve. I'm given the equivalent length of one 90-degree elbow. And so that is where my 12.5 and my 8 come from. I divide that by the diameter of the pipe on the suction side. Right, multiply that by V bar squared on the suction. V bar squared divided by 2 times gravity. And then I add the pressure term. Right? Again, 2 biggest things that popped up. 1, this has to be in PSI absolute. So not only do I need to convert it from pascals to PSI, I also need to make sure that I am accounting for the fact that what you are given in the problem is a gauge pressure, not an absolute pressure. You have to take that gauge pressure and convert it to an absolute pressure. And then make sure that that pressure itself is PSI absolute. This is what that conversion factor is for. The 2.13 is a conversion factor that converts PSI to feet, because my total dynamic suction head, the units on that are feet. So I have to plug in an absolute pressure into that term. When I do that, I should get a value of around 19 feet for the total dynamic suction head. The next important part is to calculate the net positive suction head required, which is simply taking my HS value, my P vape, right, my vapor pressure, stumbled on that one. My vapor pressure here I was given as 3.91 PSI. That gets plugged into my equation, and I calculate a net positive suction head available of around 7 feet. So, the last thing I need to do is I need to come over to my chart at 900 gallons, move up to the curve for net positive suction head required, and I get a net positive suction head required somewhere between 20 and 22 feet. So I take that 22 feet, I put it into my equation, right? And if I look at my number here of 7.21, that is much, much smaller than my net positive suction head required plus my safety factor of 2 feet. And so, because of that, I will have cavitation in my system. So, a couple of things that I saw here was getting to this part where I've calculated my total dynamic suction head and saying that my total dynamic suction head is greater than, I don't know what happened there, is greater than my vapor pressure. Therefore, no cavitation will occur. Yes, what you're referring to is correct, that at this particular pressure, that is larger than the vapor pressure of the fluid. And so, therefore, cavitation should not occur. But what you are not taking into account is the total dynamic suction head, the total dynamic suction head is a measure of the absolute pressure on the suction side of the pump, right at that suction port. There are still internals of that centrifugal pump. That's why we calculate this net positive suction head available. Now, if you had gotten to this value for net positive suction head, for total dynamic suction head, and let's say you calculated it and the pressure that you calculated here was the opposite, then no, you do not have to continue on to calculate the net positive suction head available, because it will definitely be less than the net positive suction head required. This correction here is going to lower, or is going to be lower than this value that I've calculated for my total dynamic suction head. So I can't simply base my answer off the total dynamic suction head and the vapor pressure if the total dynamic suction head that I calculate is a larger pressure than that of the vapor pressure. I need to continue on and calculate the net positive suction head available and compare that to the net positive suction head required. Part B, you are given HS. Assume an HS, assume an HD, and you are asked to calculate the cost of running the pump for a single day. What I need to do is first calculate a total dynamic head. That is fed into my equation here. My capacity is fed into the equation there. Here, I have the specific gravity of my fluid. Here is my conversion factor if I have plugged in all of my units correctly. And here is where one of the biggest issues popped up. This is the efficiency of the pump. What I told you was that the motor was 100% efficient. If the motor has an efficiency of 1, that implies that the brake horsepower is equal to the input horsepower, or the value that I need to use to calculate the electricity cost of running the motor, which then runs my pump. This value I need to get from my pump curve. Right, so I'm somewhere, I just calculated 50 at 900. So I'm right about here. That gives me an efficiency somewhere between 75 and 80. So pick 77, pick 78, pick 76, something in between those two numbers. That is the value that I plug into my equation to calculate the brake horsepower. And I can then use that brake horsepower to calculate the total cost of running my pump. Why can't I read the brake horsepower directly off the pump curve? Excuse me, not this. I cannot read the brake horsepower directly off the pump curve because of that specific gravity. Right? The pump curve is based on pumping water. That water has a particular density. So if I pump something with a density different than that, then I need to account for that in the power cost. The viscosity differences, right, those are accounted for if I pump or am pumping a more viscous fluid. Right? If the viscosity of my fluid that I was pumping here were higher than that of water, I would need to correct the capacity. I would need to correct the total dynamic head. Right? But I can't simply pull the brake horsepower off that pump curve unless the specific unless the specific gravity of my fluid is 1. Then I can simply pull that value off the pump curve, which I believe is somewhere close to 15, and do my calculation based on that. A number of you just pulled it directly from the figure, and the thing that you did not account for was the fact that the specific gravity of my fluid is different. It's lower. The density of water, the density of the acetone is lower than that of the water, and therefore you need to account for that when calculating the brake horsepower needed to achieve that capacity. And again, the second biggest thing I saw, let me change pins. The second thing I saw was plugging in the efficiency of the motor. That is incorrect. The efficiency of the motor goes there. And so if that's 1, these two things become equal to each other. So here this is all equal to the input horsepower, and that is used to calculate the electricity cost for running that pump for a single